Hi, today I'll tell you about some new group-theoretic constructions of high-dimensional expanders. So high-dimensional expanders can informally be thought of as expander graphs with some kind of extra expansion property. And these objects have been of interest in several problems where expander graphs have fallen short. So for example, they've motivated lines of work leading to recent breakthroughs in analyzing the mixing of Markov chains and improving the existence of locally testable codes and quantum LDPC codes. But despite their utility, there are very few examples of these objects known. So this motivated us to find some new examples of high-dimensional expanders, and that's what I'll tell you about today. Now, before we get to high-dimensional expanders, let me review their low-dimensional counterparts, expander graphs. So informally, these are very well-connected graphs. So for example, if you take any two large enough subsets in an expander, there will be many edges going between them. And we're going to be interested in these graphs when they're sparse, so say d-regular for some fixed constant d. So a little bit more formally, if we're given an undirected graph G, we will quantify its expansion through the eigenvalues of its adjacency matrix. So recall, this is just the 0, 1 matrix whose ijth entry is a 1 if ij is an edge, and this entry is 0 otherwise. Now, since this matrix is real and symmetric, it'll have n real eigenvalues, lambda 1 through lambda n, ordered largest to smallest. If G is d-regular, then the largest eigenvalue, lambda 1, will be equal to d, and this corresponds to the all ones eigenvector. It turns out that the gap between lambda 1 and the second largest eigenvalue, lambda 2, will be a great proxy for the expansion of G. So the bigger this gap is, meaning the smaller lambda 2 is, the better expanding G is. So we'll say that G is an epsilon expander if lambda 2 is at most epsilon times d. Now, we're not interested in a single expander graph, but really we're interested in a family of expanders with the number of vertices going to infinity and epsilon and d fixed. It's been known since expanders were first studied by Pinsker in the 70s that such families of graphs exist, and since then they have found many applications, for instance, to coding theory and to de-randomization. But they're very useful objects in many areas. Now, there are several ways that people have extended this definition from graphs to hypergraphs, or simplicial complexes. In this talk, I'll just focus on one of these, and that's this notion of local spectral expansion introduced by Oppenheim. And to keep things simple, I'm just going to give a graph theoretic definition of this. And I'm just going to focus on the two-dimensional case of our work. So for this definition, let me first define the link of a vertex as the induced subgraph on its neighbors. So for example, if we take this vertex circled on the left, then its link is just going to be this path graph on the right. Okay, so we'll call a graph X an epsilon high-dimensional expander if the links of all the vertices in X are epsilon expanders for some epsilon strictly less than 1/2. Now at first, this condition epsilon strictly less than 1/2 might look a little bit strange, but as we'll see on the next slide, it's necessary for applications. So for correctness and simplicity, I'm going to assume that all of the links in X have the same degree, d prime, and I'm also going to assume that all graphs are connected throughout the talk. And just like with expander graphs, we're not interested in a single high-dimensional expander, but we're interested in a family of bounded degree growing HDXs. Now, as I've defined them, it's not clear in what ways these objects are high-dimensional, or even in what ways they're expanders. So far, they just look like graphs that kind of have little expanding neighborhoods. But the connection to expander graphs is given by this theorem of Oppenheim, which has its roots in earlier work of Garland. And this theorem states that an epsilon HDX is actually an epsilon over 1 minus epsilon expander graph. So HDXs are expanders. And note here that when epsilon is at least 1/2, this gives you something that's at least 1, which is trivial. So this is one reason why epsilon being strictly less than 1/2 is interesting. And it turns out there are simple examples where all links have lambda 2 or epsilon equal to 1/2, and these graphs do fail to expand. So less than 1/2 is necessary. Now, to see how these objects are high-dimensional, or why we might call them high-dimensional, first recall the random walk, the lazy random walk on the vertices of a graph. So starting from some vertex, we will pick a uniformly random edge containing the vertex, and then move to a uniformly random vertex in that edge, and keep repeating this. This gives us some walk on the vertices of the graph, and if the graph is a good expander, this will mix quickly. So after a small number of steps, we'll expect to be at each vertex with roughly the same probability. And here I'm ignoring the distinction between one-sided and two-sided expansion. Now we can define an analogous random walk on the edges of a graph. So starting from some edge, you can just pick a uniformly random triangle containing it, if there is one, and then select a random edge in that triangle, and so on. And it turns out that if we have a high-dimensional expander, then not only will this random walk on the vertices mix quickly, but this random walk on the edges also will mix quickly. So that explains the name high-dimensional. Okay. The next question is if these objects even exist. And it turns out this is not such an obvious question. So for expander graphs, it's not hard to show that a random graph will be a good expander with very high probability. So you might ask, okay, if you take a random graph, is it a good HDX? Well, we can try, and let's say we consider the model of random graphs where each triangle is included with the same probability, p. And if we want this graph to be deregular, or regular, we should take p to be proportional to 1 over n squared. But now let's consider what the link of a vertex looks like. So each vertex is just going to be contained in a constant number of random triangles. And so its link will probably just be a matching, which is not connected, let alone an expander. But HDXs do exist, and the gold standard for them comes from these Ramanujan complexes constructed by Lubotsky, Samuels, and Vishnay, and these generalize the Lubotsky-Phillips-Sarnak expander graphs. So these have much stronger expansion properties than what we asked for, actually. And similar examples can be found in earlier work of Cartwright, Soleil, and Jouc. So this construction uses somewhat pretty sophisticated algebraic machinery, and this led researchers to ask if there is a more elementary construction. And such a construction was given by Kaufman and Oppenheim in 2018. So they gave a completely elementary group theoretic construction. And this was the starting point for our work. So now I'm going to describe this construction and tell you how we were able to generalize it. So the core tool in this construction of Kaufman and Oppenheim is a concept from group theory called the Coset complex. Given a group G that's generated by subgroups H1, H2, and H3, we're going to define a graph, which will denote XG, H1, H2, H3. And the vertices of this graph are just going to be the cosets of the three subgroups of G. And we're just going to draw a triangle between a triple of cosets whenever they have a common intersection. So whenever some element is contained in all of them, we draw a triangle. Now, note that since the cosets of a subgroup partition the group, each triangle will involve one coset of each of the three subgroups. So this graph is going to be tripartite. So as a very simple example, let's see what happens when we take G to be the direct product of Z5 with itself 3 times. And we take HI to be the subgroup whose ith coordinate is 0 and other coordinates are allowed to be anything. Okay, so then the cosets of the subgroup HI are just going to be sets of points with a prescribed ith coordinate, and where the other coordinates are allowed to take on any values. So we can visualize this if we think of G as a 5 by 5 by 5 cube of points. Then these cosets will be axis-aligned planes. And now if we take one coset of each type, one plane of each type, they will always intersect at some point. And so we'll have a triangle between them, and therefore this coset complex is just going to be the complete tripartite graph. Now, one simple observation is that this graph is going to have bounded degree just when the subgroups have constant size. Another simple observation is the number of vertices is just the number of cosets of the 3 subgroups. And therefore, if the size of the subgroups is fixed, but the size of the group that they generate is going to infinity, you're going to get a family of growing graphs with bounded degree. Okay, so we're searching for a family of groups that are growing in size, but they're generated by 3 small constant size subgroups. Okay, and the final ingredient for a high-dimensional expander is expanding links. So it's not really clear at first how you should go about getting this, but maybe one idea would be that one of the ways we know how to construct expander graphs is by looking at Cayley graphs of groups, and in particular Cayley graphs of groups of Lie type, or matrix groups, or Chevalley groups, really like to expand. So for example, an example of such a group would be the special linear group. So maybe by taking G to be some matrix group, maybe the special linear group, and picking the H's in some clever way, we can get expanding links. Okay, and this was done in this construction of Kaufman and Oppenheim. So they took G to be SL3Q, the group of determinant 1 matrices, 3 by 3 matrices with entries in FQ, where Q will be equal to the prime power P to the M for us. And then they take H1 to be the subgroup of upper triangular matrices with 1s on the diagonal, and where the entries just above the diagonal are linear polynomials, and the top right entry is a quadratic polynomial. So here, when I refer to the entries as polynomials, I'm using the fact that we can identify elements of fp to the m with polynomials of degree less than m with coefficients in fp. Okay, and H2 and H3 are chosen similarly, as is shown. Now note that the size of each subgroup is p to the 7th, since we have p squared choices for each linear polynomial and p cubed choices for the quadratic polynomial. It's also not hard to show that these three subgroups actually do generate the group G. Now, since there are q to the 9 3x3 matrices with entries in FQ in total, and since SL, this determinant equals 1 condition, imposes one constraint, the group has size roughly q to the 8, so we lose a dimension basically. So the idea is that if we take P fixed, these subgroups have constant size, and then if we let M grow, the group that they generate is going to go off to infinity. So this gives us a family of bounded degree graphs that are growing. So what Kaufman and Oppenheim showed is that the links of this coset complex are 1 over square root p expander graphs when p is greater than 2. So this gives us our first example of a HDX family. So we extended this result by giving analogous constructions that work when G is any matrix group, not just the special linear group. So here, when I say matrix group, informally what I mean is a set of matrices over FQ that are defined by polynomial equations and that happen to form a group under the operation of matrix multiplication. So this will include finite analogs of groups that maybe you're familiar with, such as the orthogonal groups and the unitary groups and the symplectic groups. A little more precisely, what I mean are the untwisted Chevalley groups, not including the exceptional group G2 of Q. So our key example is the following construction, and it turns out that all of our other constructions in some sense follow from understanding this one example. So for this construction, we take G to be the symplectic group, SP4Q, and this is the group of 4x4 matrices A, satisfying the equation AX A transpose is equal to X, where X is the matrix pictured here, where the upper right block is a 2x2 identity matrix, and the lower left block is a minus identity. And it turns out that the following matrices of the following form of the form H1 form a subgroup, and similarly for H2 and H3. And in fact, these elements of this form will generate the group G. So these are three subgroups that generate G. They're a little more complicated looking than the previous ones we had on the last slide. So for example, we now have some entries C appearing, where C stands for cubic polynomial. But it's not too bad. And what we showed is that if you fix some p greater than 3, then the coset complex corresponding to this group and this choice of three subgroups is a square root 2 over p high dimensional expander. So contrast this to the 1 over square root p example of Kaufman and Oppenheim. Okay, so let me now say a few words about how we prove this. So the choice of subgroups on the previous slide, this might look a little bit mysterious, but it turns out there is a very clean way to understand them. So the key to this is the fact that these Chevalley groups have a piece of data associated to them called a root system. And this root system is used to define something called the Steinberg presentation for G. So using the Steinberg presentation, we can give very clean descriptions of these subgroups. Unfortunately, when written as matrices, they can get very complicated. And using this presentation, we also show that this choice of subgroups we make generates the group G. But in general, the description of the subgroups is very clean in terms of, it's described very cleanly in terms of the root system. Now, in my opinion, the fun part of the work was showing that these links are expander graphs. So using this Steinberg presentation, we obtain very simple and explicit descriptions of the links. And ultimately, there are only ever three kinds of graphs that can arise as links. So the first one is the complete bipartite graph. And this is the best expander we can hope for, since it has lambda 2 equal to 0. Or we might get a 1 over square root p expander, and this was the graph that's analyzed in the construction of Kaufman and Oppenheim. Interestingly, this graph can be seen as a variant of the point line incidence graph over the vector space fp squared. And this graph has shown up in a few different areas at least. So it shows up in bounds on the sum product problem in finite fields, and also in the zigzag construction of expander graphs. So finally, we can get a slightly more complicated square root 2 over p expander graph, and that's what we analyze. Now, the punchline is that we can relate all of these graphs to Cayley graphs of abelian groups with certain nice sets of generators. Then, by expressing the eigenvalues of these graphs as character sums, we're able to give very elementary bounds on the eigenvalues. So at the end of the day, we just use the Schwartz-Zippel lemma to bound some character sums. So the expansion is elementary in the end. Okay. So today we've seen that HDXs are some kind of strengthening of expander graphs, and they seem somewhat difficult to come across. However, we have this construction where we take a group and a choice of some number of subgroups, and this produces something called a Coset complex. And Kaufman and Oppenheim showed that using the special linear group as your group, you can obtain high-dimensional expanders. And we showed more generally that an analogous construction works with basically any Chevalley group.